Hey, hello everybody. Today is going to be kind of a short day because we're going to talk about hyperbolas. And hyperbolas are so closely related to ellipses that most of the explanation that you need for them was already talked about in the last video. So we'll be able to move through this pretty quickly. Uh, Hyperbolas are essentially, I'm going to say something that's a little bit, um, I don't know, probably not PC in the math community is essentially an ellipse that's been kind of split in half and turned in the other direction. And I say that that's not uh, PC because technically the hyperbola is going to go on forever in those directions. Um, but for the viewing windows and the way that we look at it, and the way that we think about it, I think it's a good way to think about it, especially because their equations are so closely related. Um, Now, when you had an ellipse, pretty much the definition of an ellipse was a specific object that had two foci, and every single point had to be a constant distance, d1, d2, and the sum of those two distances on any point on the ellipse must have equaled a constant number. So regardless of where you put that point, the sum of d1 and d2 would always be some constant. And the same type of relationship is true for hyperbola, with the exception of the fact that those two distances must be related in the way that d2 minus d1 is that particular constant. So it's not the sum of the two distances that makes a constant, it's actually the difference. And we're going to see that that's essentially the type of relationship and the way that the ellipses relationships change. They just become like a negation of the same relationship. So a little bit of vocabulary about hyperbolas before we jump into anything. The two parts, the two separated pieces are called branches. And those two branches are parabolic type shapes, and they go on forever, each with its own focus kind of within the branch. Now there's still this axis in ellipses. We had a major axis and a minor axis. In a hyperbola, we have an axis that travels through the foci, through the vertices of the hyperbola, through the center of the hyperbola, and this one axis is called the transverse axis. Um, and of course, the midpoint on the transverse axis between the vertices, between the foci, is the center. So we still have the same relationships for things with A, B, and C, just like we showed on the ellipse. And they mean the same things. They're going from the same places, but their relationships are different because their sizes are different. If you can recall to the ellipse, the major axis, that long axis on an ellipse, was labeled A or 2A. Half of it was labeled A, and it was generally the longest piece. In a hyperbola, A still goes from the center to the vertex, but unlike an ellipse, the center to vertex in a hyperbola is quite small. It's definitely small in relationship to the center to the foci, which center to foci in an ellipse is generally quite small, but in a hyperbola it's much larger. So we have a different type of relationship when we create that equation. Like we had an a squared equals b squared plus c squared type situation in the last one. Uh, that's going to be different in this case. So let's look at the equations. As you can see here, they're almost identical to an ellipse. The only difference that we're going to have is, like I was saying before, negation, subtraction. And that's what's really going to distinguish an ellipse from a hyperbola in terms of looking at their equations, is the subtraction there. This is what I was talking about on the last slide, which is their relationship between the two, between the values of A, B, and C in the equation. The relationship here actually is very much more Pythagorean. C squared equals A squared plus B squared, which might actually make it easier to remember or to comprehend. So let's jump into an example, and we'll be able just to see how similar these two hyperbolas are to the processes for ellipses. So again, we're faced with a situation where we're not given very much information. It's very limited. We're given where the foci are, and we're given where the vertices are. So from that information, we're trying to build a standard form equation. Now, much like we did with an ellipse, one of the first things that we need to do is get the center, because obviously the center gives us in the form of the equation we have x minus h squared, and depending if it's going to be with a transverse axis vertically or the transverse axis horizontally, we'll either have a or b under here, and then minus y minus k squared over b squared. And again, the a and b might switch depending on which way the axis is going, and that's going to equal 1. So the h and the k, the center point, is very, very crucial to making the equation. So that's one of the first things I want to go for. And again, I'm just going to find it by midpoint formula. And let's just make a very crude drawing over here. -1, 2, and then 5, 2. So these are kind of where my foci are. And you'll be able to, pretty quickly tell that your center point is just going to be at 2, 2. You don't really need distance formula in this case. It's pretty easy. Alright, so you have your center point, and from the center point you're able to get A and C, because A is going to be the distance from the center to the vertex, and C is going to be the distance from the center to the foci. So the vertices are supposed to be at 0, 2. I'll put those in blue here so I can distinguish. And it's supposed to be at 4, 2. Okay, so it looks like this thing is going to be going kind of in that type of way. It's probably not exactly what it's going to look like, but that's somewhat the shape. That way we know, okay, the transverse axis here is going horizontally. So I need to make sure that I'm doing the correct equation for a transverse axis being horizontal, which in this case I do. I have A underneath the x and I have B underneath the y. Okay, so that's a hurdle to get over as well. So now, given all this information, I can find A and I can find C quite easily. A being the distance from the center point to the vertex, which if the center point is 2, 2, and this vertex is 0, 2, the distance A should just be 2 units. And C is the distance from the center point to the foci, and this foci is -1, again this is 2, so the distance between them is 3. Okay, so I have A and I have C, the only thing I'm missing is B, and I need that B in order to make the equation. So I'm going to use my relationship, and in this case, all that I have to do is the square root of B equals C squared minus A squared. So B equals square root of 9 minus 4. B equals square root of 5. Now I think I have all the information I need. I have H, I have K, I have A, I have B, and I'm ready to go. I know that I'm using the correct equation because my transverse axis is horizontal. So here we go. X minus the H value, which is 2, squared over A squared, so 2 squared, minus Y minus the K value, which is 2, squared over the square root of 5 squared equals 1. And I'm done. If I go to the next slide here. Alright, it looks like I had a pretty good idea of what the whole thing was going to look like. if I do it out on a graphing calculator, it's definitely a much better solution. But I do have the right equation here, and that's what's really important. Go to 9.3, check out example or exercise 39. Try that one out on your own, and I'll check over it in class. And once you're done with that, I only have one more example I want to work through. Alright, so hopefully that exercise wasn't too difficult, and moving on to this next example will be just as easy. I don't think that we can really do enough examples of trying to go from a form like this into the standard form of whether it's a circle, ellipse, or hyperbola. So I definitely want to make sure that we do another example like this, because it does involve completing the square. It does involve moving things around a bit. I think that it's important. So what we're going to do is start with the original equation and try and get it into standard form of a hyperbola. And let's remember that that's going to be x minus h squared over a squared minus y minus k squared over b squared equals 1. So let's keep this in mind and try and make all of our moves with this this plan. Okay, so first off, what is it that we can possibly do to try and make this thing work? Well, I know that this 16 is going to get in the way. I know that because I'm going to have to complete the square over here on both of my x and my y to make this factorization happen. So I'm going to move the equation a little bit so that it says 4x squared plus 8x to get the x's together, minus 3y squared, and then I'm going to move this 16 to the other side. Alright, now I'm getting it in a little bit better way so that I can complete my square. Now I'm actually going to take out a 4 here. That way I have a perfect square trinomial that I can build. And then I'm going to go ahead and complete the square. So over here, what do I have to do to complete the square? I have to take the 2, divide it divide it in half, and then square it. So divided in half is a 1, squared is still a 1. But the fact that I have a coefficient of 4 over here means that I also have to multiply it by 4. So what I'm going to have to do is I can complete my square here, 4x squared plus 2x plus 1 minus 3y squared equals plus 4. Alrighty. And now in my last one I can start to factor it down, 4. And then this whole thing is going to factor down to just an x plus 1, nicely, just the way I wanted it to. Squared minus 3y squared equals negative 12. Now, do I have to do anything with the y? Because normally I would be completing the square at the same time, but I actually don't need to do anything with this one, because technically what this is going to show me is that it's 3 times y minus something, and that y minus something, that something is a 0. So there's nothing here for me to do. This is just showing me that the k value is a 0. Alright, so I don't need to worry about that. The next thing that I want to do now is, what do these things show me? It shows me I don't have a coefficient here, first of all, and I don't have a coefficient on the y either. So I really want to get rid of those. And the way that I'm going to get rid of those actually helps me out in terms of changing this to a positive 1. So what I'm going to do is I'm going to divide everything by negative 12. What does that do? Over here it gets me a 1. And then over here it's going to change things up a little bit for me, but it's going to give me my a and b values as well. And it's also going to change this one negative. So my first term is going to be positive y squared over 4, or I'm going to call that 2 squared, because I want an a squared term. and then it's going to be a negative. Say it's going to be x plus 1 now, squared, over, and what happens when I divide 4 by negative 12? Well, yes, it became negative, and down on the bottom here I'm going to have a 3, but I want it to also be a squared term, so I'm going to make it the square root of 3 squared. That's the same way as writing 3, what would generally be underneath there, but I want to write it as a b term squared. Okay, and this actually is my finished product. This tells me all that I need to know, my a, my b term, my h, my k term, and we're done. We've transferred it into standard form. All right, try exercise 25. It's going to ask you to do a little bit more than change it over into standard form. It's going to ask you to find asymptotes for the hyperbola, and I would like you to try that. The formulas for asymptotes are on page 658, and it's essentially taking a, b, and k values and just plugging them into an equation. So it's not too difficult. I'd love you to try that. So exercise 25 from 9.3. Good luck, and I'll see you guys next time.